there, stats enthusiast. Welcome back to our AP Statistics series. I'm Goldie, and today we'll be focusing on an activity where we are going to be simulating the sampling distributions of a sample proportion. This activity will serve as a great introduction into understanding the differences between the population distribution, the sample distribution, and the sampling distribution. We are going to simulate all three of these concepts, bringing them to life, and giving you a hands-on experience that will really solidify your understanding of sampling distributions. So whether you are following along with your own simulation resources or you're just tuning in to try to get a better understanding of these things, let's get right into it. We are going to be running a simulation of the sampling distribution of a sample proportion today. And to set up our simulation, we are going to be imagining we have a cup of 100 cards. Now, you may or may not have these cards in front of you. If you do, that's awesome. You can work with them as we go through. If you don't, then you can just follow along and imagine these cards are in front of you. So in this bin, or in this cup of 100 cards, 50 of the cards have a check mark, and 50 of the cards have an X on them, as in the visual you see on the screen. So 50 each. And in this activity, we are going to be interested in recording the number of check marks in our samples. So that's going to be our success. So as we would say, our proportion of success. So there's 50 of each in our bin here. Now this bin or this cup, this represents our total population. It's the number of cards. We use a capital N to talk about the size of our population. And for us in this simulation, it is going to be 100 cards. Right? Populations come in all sorts of shapes and sizes, but for us in this simulation, it is going to be 100 cards. Lowercase p is going to be our population proportion. So that represents the proportion of successes we are interested in the entire population. So for us, we're interested in the number of check marks in the population. And we know that there are 50% check marks in our population. So p is going to be equal to 0.5. So this is all information on our population. So now we're going to simulate a sampling distribution by taking repeated samples of 10 cards from our population. So if you've reached this point, you may or may not know what a sampling distribution is, but we are going to be experiencing it by running the simulation, and then we're going to talk and formalize it after we experience it. Okay, so this is the setup for the activity. So we're not going to be taking data yet. I just want to explain what the activity is going to look like. So from our cup of 100 cards, we're going to randomly choose 10 cards from this cup without replacement. So we pick out 10 cards and we don't put them back after we have picked. So if we pick one, then we pick the second one without replacing the first one. We take out 10 cards, and we're going to record in our table how many check mark cards we pull out. We'll keep track with a tally in our table to record how many in each of our samples, how many check marks there are going to be. After we record that in our table, we put 10 cards back. So we are going to put them back into our population so that our population size once again becomes 100. We're going to shuffle them up very well, and then we're going to repeat it again until we have performed 20 trials. So 20 trials, that's going to be how many times we are going to run this simulation. So here is the table that I have. I have number of check marks out of 10 cards. And then in the trials, those are left blank. I'm going to put a tally mark in those. Okay, so I'm going to record how many check marks. So 0 is my lowest possible, right? If I pull out all X's, I have 0 check marks, or I could pull out 10. I could pull out all 10 green checks, right? That's definitely a possibility. and we're going to do it 20 times to see kind of where my samples are going to fall here. Okay, so let's do it first. All right, so I'm going to take out 10 cards. So here's me simulating taking out 10 cards, and I'm going to count up the number of check marks. So you can see in my sample I have 1, 2, 3, I have 4 check marks. So I'm going to put a tally mark under 4. Okay. Now that I have those 10 cards, I'm going to put those 10 cards back into my cup. I'm going to shuffle that well. Okay. And now I'm going to do that again. I'm going to repeat. So that one tally mark was one trial. I'm going to do this 20 times. So I'm going to take out 10 more cards. I'm going to count the number of check marks. So here I see I have 7 check marks. Okay. And then I'm going to put them back in, and I'm going to repeat that. Okay. Now, if you have the cards in front of you, you can go ahead and pause the video and do this yourself and get your own sample data to see what is going to happen. If you don't have the cards, we can definitely talk about it. I do have data already available, so I don't have to redo this slowly on the video again. But we are going to see what happens just after 20 trials. I want you to first think about what you expect to happen after 20 trials. So before I show you the data here, what do you think? Well, we know our population. In our population, our proportion is 50% check marks. So if we are pulling out 10, would we expect that proportion to be 50%? I mean, maybe your intuition kind of tells you that, right? Hopefully, maybe. Maybe it does, maybe it doesn't. It'll be B5. But what we saw with our first 2 trials is it wasn't 5, right? It wasn't perfect. It wasn't exactly 50%. But we didn't think anything was amiss. You know, we didn't call me a liar or anything like that. So what are we experiencing here? Well, we're experiencing a very exciting thing called sampling variability. Okay. So here's my data. I already did this activity off screen. I did it 20 times, and here are my my results. So each tally mark represents a sample of 10 that I have picked. Okay, so I can see I didn't really get anything. I got nothing in the extremes here. I can see I got low number of trials out here. They're all kind of centered right around here in the middle. Okay, now what I would do if I was in class, this is my data. What I would do if I was in class is I would compile the entire class's data, okay? Because this is just 20 trials. If we combine the entire class's data, I get many more trials. And that's what I'm going to show you in this next table here. So I still got my top row, number of check marks out of 10 cards. Now I'm going to bring this just into a proportion. Okay, so I didn't do anything fancy. It's just the proportion of check marks in my sample and the number of trials. So I'm going to compile my class data. So this is actually data from 7 students, I guess myself included. So 6 students plus me, for a total of 140 trials. Okay, 140 trials, and instead of making 140 tally marks, I'm just going to show you the numbers that go there. Okay, so we're compiling the class data. So in this simulation, remember, a simulation is something we repeat over and over again to model a chance process. So we repeated this over and over again to model this chance process of picking 10 cards from a population of 100. So again, you can see that right around here is where the majority of my trials ended up falling. As we go farther away, I get less trials that have those extreme values. And again, that's just kind of what my intuition is sort of telling me, because in my population, the proportion is 0.5. It is 50%. And intuition would tell me, okay, like, yeah, it's possible to get 9 out of 10 check marks, but not very likely in 140 trials. Okay. So a lot of this this intuition you have about sampling distributions is already there, which is great. We're just kind of experiencing it now. and we're going to kind of formalize what we're going to see, what we're seeing in a moment here. I'm going to take a second and define some key vocab about sampling distributions, some vocab and symbols specifically that you have to keep straight. So when we're talking about a number that describes a population, we are talking about a parameter. So think of parameter P and population P. Okay, parameter, population. A parameter describes a population. There's three numbers or three values that are going to describe a population. Capital N describes the total population size. Okay, so we talked about that at the beginning of this activity. Lowercase p describes the total population proportion. In some texts, you might see that represented as a capital pi or a lowercase pi, just depending on the text. But we tend not to use that just because we don't want that to get confused with the constant pi, the 3.1415 exciting constant there. So we don't use pi in this class. We are going to use lowercase p to describe our population proportion. And then mu here is going to describe the total population mean. Now, this simulation is centered around population proportions. Okay, population proportions. We're going to get to means in a couple lessons here, so don't worry too much about the means, but mu describes the population mean. When we get to sample data, that's what we call a statistic. So think an S, think sample. Statistic comes from a sample, and the numbers we get from a sample include lowercase n, which is the sample size. It includes p hat, which is the sample proportion. So that's how we pronounce that symbol, is p hat. That's our sample proportion. And x bar is going to be our sample mean. Again, we're not working with means quite yet, but I wanted to put this in here to kind of summarize parameters and statistics for you. P hat is going to be the sample proportion we are going to be focusing on. So in our activity, we chose cards from a population of 100. 50% of those cards were check marks. That is a fact about our population. In one of the samples, a group got 3 out of 10 cards to be check marks. Okay? Now, which of these numbers are population parameters and which are going to be sample statistics? So population parameters are numbers that describe the population. So we know that the total number of cards is 100, so capital N is going to be 100, and lowercase p is going to be 0.5. Okay, so those two are going to be our parameters. What numbers are our statistics? Well, lowercase n, we took a sample of 10 cards from our population, so that's going to be 10, and p hat is going to be 0.3. So p hat always describes a proportion. So we got 3 cards to be check marks, but whenever we describe a proportion, we want to make it into a decimal. So p hat we got from taking 3 out of 10. Okay, so 0.3 is going to be p hat, our sample proportion. Okay. All right, now let's bring this simulation kind of full circle here and talk about what we have created. We've actually created 3 different distributions. And what are those? Okay, well, one of them, spoiler, is going to be a sampling distribution. Before we get there, let's talk about that term I brought up earlier, sampling variability. And I called sampling variability kind of a natural intuition about taking a sample. When we took repeated samples of size 10 from our population of 100 cards, we knew that in the population, we had 50% green check marks. So we kind of would expect 5 cards out of our sample of 10 to be check marks. But we saw very easily that it wasn't the case. Okay? And we also understood that that was okay. We didn't expect any sort of lying going on or cheating. We know that that's not going to be the case every time. We're not going to have exactly 0.5 green check marks coming out. And that's the idea behind sampling variability, is that when you take samples from a population, Even though we want the sample to be sort of a mini population in itself and kind of look like a population, it's not always going to, and that's totally fine. That's just natural sampling variability. So the first distribution we came up with is our population distribution. So this refers to the distribution that our population takes, right? So we've said this plenty of times now that P is 0.5, the proportion of check marks. Now there is a single population distribution for each unique situation. So our situation here with 100 cards, there is one single population distribution. And this is what it looks like if I were to graph it, right? It's categorical data, so I have a bar chart, okay? And this is what it looks like. 50 check marks, 50 X's, one single population distribution. The next type of distribution we created was a sample distribution, and this refers to the distribution of each individual sample of 10 cards. And the sample distribution will vary. Okay? It'll look different from sample to sample. In our example, one example, we took out 10 cards, and 3 of them were check marks and 7 of them were X's. And if we were to graph it, this would be what it looks like, right? This was an SRS, a simple random sample. N was our sample size, and our proportion of check marks was 0.3. The next sample I took, I could get 6 check marks and 4 X's. So again, N would be 10, and my proportion, P hat, of success would be 0.6. Okay. Now I could graph every sample that I took. How many did I take? Well, when we compiled the class data, we took 140 total trials. Okay. So we have 140 sample distributions in our simulation. Okay. Now that's specific to our simulation. In I guess the real world, if you want to call it that, the number of sample distributions you can have is infinity, right? You could do this until you're old and gray, okay? There is an infinite number of sample distributions you might take. Just in our simulation, we did 140. So this will vary as you go through. Now, finally, we get to the big one, the sampling distribution. Okay, what this unit is all about. We're finally here. Now, what is the sampling distribution we created? Well, this is going to refer to all possible sample statistics, P hat being the sample statistic we gathered, put together in a single distribution. So in our simulation activity, we're going to approximate the sampling distribution and check out some of the properties that it has. So our sampling distribution that we're about to graph here is an approximation because we only did 140 sample distribution, sample statistics, but in reality, it's all possible sample statistics. It's an infinite amount, right? So if we take every P hat from each of those sample distributions we had and put it together, this is the graph we get, right? Proportion of check marks, and then the frequency each of them took. So now notice we went from a bar graph into a histogram because we're no longer dealing with categorical data. Now we have quantitative data. P hat is a quantitative value. Okay. So this is our approximate sampling distribution. A true sampling distribution takes on all possible P hats, but this simulated sampling distribution is going to highlight some key features of all sampling distributions. And that's what we're going to discuss in these last couple of questions in our activity. So first, describe this, right? Describe what you're seeing here. So if you're given a graph and you're asked to describe what it is, remember we have to comment on 4 things, right? Shape, outliers, center, and spread. So the shape, to me, this is unimodal, and it definitely appears approximately normal, right? If you were to draw a line through the top of all of those, you would see that we would have an approximately normal looking curve. Okay, so approximately normal is what we will say for that shape. Outliers, there's no visual outliers here, right? We don't have to do the outlier test for this. We just want to comment on if there's any visual outliers, and there's not. Center and spread, we can find the mean and standard deviation. Now we're going to find the mean and standard deviation because our data appears unimodal and approximately normal. Remember that if you were using, if you had some sort of skewed data, you would probably want to use median and IQR to describe center and spread, but mean and standard deviation are perfect here. How do I find it? How do I find it from my data? Well, this is where the table comes in. So I'm going to bring back this table. This is what we filled out earlier in our activity. This was our class data, okay? So this was our class data. What we're going to do to find the mean and standard deviation, because this is how I made the graph, right? If that's not clear, let me go back here. I made the graph, so there were 2 trials that had 0.1. So here there were 2 trials that were 0.1. There were 6 trials that were 0.2. Okay. There was 8 trials that were 0.3, and so on and so forth. So that is how I made this graph. I made this graph from this table we had earlier. Okay. And now to find the mean and standard deviation using that table, instead of entering each individual value into a list, because there's 140 values, I can take advantage of my frequency list. So in L1, I'm going to put all of my proportions, and in L2, I'm going to put the frequency, how often it takes those proportions. So L1, L2. And then since I have L1 and L2, again, these are in my calculator here, I'm going to go to 1-bar stats on my calc. My list is going to be L1, and my frequency list is L2, right? How often do I have those values? Okay. And if I press calculate, I will be able to get my statistics. My mean is going to be X bar right here, and my standard deviation is going to be S sub X right here. Remember not to use sigma sub X. That's a different formula for the population standard deviation. So we're going to use S sub X. Okay, those are my 2 values. That's my mean, and that's my standard deviation there. Now, if we wanted to do complete AP statistics speak as we would on a free response question, we have to make sure that we take this information and we put it in context of our proportion of check marks. Okay, so here's a little blurb right here of how we can take that and put that actually with some context. All right, so remember that shape, outlier, center, spread. You can list it, of course, but to get full credit, you want to make sure that you put the context with it. Okay. So now here's the description of our simulated sampling distribution, but what else does it really tell us? Okay, how does our population proportion relate to the sampling distribution mean? Okay, so we're going to look at the means, and why do we think this is? Well, the sampling distribution mean 0.512 was very close to our population proportion of 0.5. Okay, very close. And again, this was a simulated one, but it still ended up pretty close. And this is because though we expect each sample to vary, right, as we take each sample, we expect it to vary. We expect that natural variation. Over many trials, we would expect the proportion of those cards being pulled to be 0.5 as a long-term average. And we talked about this with proportions, right? If you go back to when we talked about like the flipping coins, right? If we got something like this, if we flipped a coin 5 times and got tails and then 4 heads, we wouldn't necessarily think, oh, the coin it's an unfair coin or anything like that. What we would expect is if we continued flipping the coin, the long-term average, it would even out. And it would be about 50% heads, 50% tails. And that's the same thing with our sampling distributions here. In the long run, we do expect the proportion of our population to be equal to the mean of our sampling distribution. Okay? And try not to let your mind be too blown by that. It is very exciting. Okay? That is a very significant piece of information for statistics. Okay. The last question, okay, because again, it's just an activity, a simulation. Let's kind of wrap it up here before we get into the next set of notes to talk about this a little bit more. Okay. Describe the concept of a sampling distribution in your own words. How does it differ from a population distribution, and how does it differ from a sample distribution? So these three distributions, you were introduced to the differences between those three today, and we're going to be talking about them throughout the next couple sections of notes, and you have to make sure you know the difference between the three, right? The sampling distribution represents the distribution of a sample proportion, and it's calculated from multiple random samples taken from the same population. Okay? That's almost a textbook definition of really what a sampling distribution is going to be. Okay? It shows all possible values of the statistic. In our simulation, the statistic was p hat. Okay? And how frequently it occurs in repeated samples. Okay? Meaning we took p hat and we looked at, okay, how often does it occur within these intervals? Okay. And we looked and we saw that it was an approximately normal distribution. We saw that the mean of our sampling distribution was approximately equal to the proportion of our population. And there's also a fun fact about the standard deviation we're going to talk about in the next set of notes too. Okay, we didn't forget about that standard deviation. We will be talking about it. It just is a little bit more of a formula for it. Now, the population distribution shows the characteristics of the entire group. And remember, there's only one population distribution. Okay? There's only one of those things. The sample distribution is the distribution of actual data, okay, within one specific sample, and it shows us the pattern of values within that particular trial. And there's many of these. Okay. Many of these. There's one population, there's many sample distributions, and there's one sampling distribution. Okay.
And there you have it, folks. We've wrapped up our simulation activity exploring the sampling distribution of a sample proportion. I hope this hands-on experience has illuminated the distinctions between population, sample, and sampling distributions. In the next section of notes, we are going to work on formally defining the sampling distribution for a sample proportion, as well as trying out some practice problems. If you found this video helpful, don't forget to hit the like button and subscribe to my channel for more statistics content. Wishing you endless statistical success. I will see you in the next video.